Hello, everyone. At first, let me thank you for coming to my presentation talk. My name is Jiří Vinopal, and I work as a threat researcher for Checkpoint Research. For today, I prepared a presentation called ReadyToRun stomping that will introduce a new method, hopefully interesting enough. So let's start. The content of the presentation will be about introduction to ReadyToRun stomping, different ways of implementation of ReadyToRun stomping, and problems that affects reverse engineers and security researchers during analysis of ReadyToRun stomped assemblies, techniques and tools that can be very helpful for reverse engineering ReadyToRun stomped assemblies, and the last section will be about detection of this technique. Usually, when we are dealing with regular .NET assembly, we just expect that this kind of .NET-P will contain just the managed code, which is also known as intermediate language, IL code, MSTIL or SIL. Once we are basically programming our application, .NET application, we are doing that with using like programming languages like C#, F#, VBNet. And during the compilation, we get something like what could be referred as .NET-PE or .NET assembly. And this file format contains our compiled source code in a form of IL code. But once we try to execute the .NET-PE, the IL code can't be run directly by the CPU. So the IL code needs to be actually compiled again into the native form of the code, assembler. And this is processed by something which we can call a just-in-time compiler, also known as JIT. And obviously, JIT compilation is the main cause of the slow startup time and the speed of the execution of .NET applications. Solution: different ahead-of-time compilation formats. Generally, ahead-of-time compilation formats are trying to reduce the usage of JIT or avoid the usage of the JIT at all. We have the main forms of ahead-of-time compilation formats that are Engine. This is just Windows-specific, .NET Framework only, and it's a little bit fragile solution. We have also ReadyToRun form, which is also the main target of this presentation. This form is supported from .NET Core 3, and it is reducing the JIT by pre-compilation of the IL code to the native code. And the last one is also the newest one. It's native ahead-of-time format, and it's supported from .NET 7. It's the real full native format, so we have like the real native PE and CPU code. There is no need of .NET runtime to be installed to run this .NET assembly or native ahead-of-time file format. There is no JIT, IL code, and .NET metadata. But regarding to the ReadyToRun format, this format contains the .NET metadata, IL code, and native version of the same code. And when I'm saying same code, I mean like same code because it's actually what we are trying to target here in this presentation talk, that it doesn't have to be the same code. So regarding the ReadyToRun assembly, the structure still is the same. There is the still same base of CLI file format that we can refer as a .NET assembly. So we see still the P headers. There is .NET directory, and there is also in .NET directory one field which is called manage native header. And in case of ReadyToRun assembly, the manage native header points to another header that is called ReadyToRun header. And this contains many structures and sections that are needed for successful execution of the precompiled code in the ReadyToRun assembly. We can see the structure here. This is a picture from .pic tool. So finally, what is ReadyToRun stomping? It's about altering the ReadyToRun compiled binaries in a way that the original IL code will differ from the precompiled native code. And because of the .NET optimization, the precompiled native code is prioritized and will run absolutely ignoring the difference to the original IL code. And there is another quite a tricky problem that the default settings of managed debuggers such as dnSpyEx differ. What does it mean? Basically, when we try to open a ready-to-run assembly in dnSpyEx tool and try to debug that, what is executed is actually our IL code that gets compiled via forced JIT. So the precompiled code of the ready-to-run assembly is ignored in dnSpyEx. The result is that we have different execution once we try to execute our ready-to-run assembly in normal execution, and once we try to execute it in dnSpyEx debugger. Of course, ready-to-run stomping is supported from .NET Core 3 to .NET 5+ across different architectures and OS platforms, so Windows, Mac OS, Linux. The implementation is about modifying the original code of the ready-to-run assembly in a way that the behavior of the IL code and the precompiled native code will differ. We can do that in two ways. First one is about replacing of the compiled IL code and leaving the precompiled native code intact. The second one is about replacement of the compiled native code and leaving the IL code intact. In both cases, we need to preserve the .NET metadata. This is really important because otherwise, sooner or later, it will result in failure during the execution. It's surprising because we will be executing the precompiled native code, which is assembler, but there are still type references in the assembler, in the precompiled native code, that need to be resolved during the runtime. So there is still dependence on .NET type references, which are a part of .NET metadata, so we need to be careful about preserving them. Here is first example. We will be replacing the IL code and leaving the precompiled native code intact. We have here like very simple C# application that just prints some text, welcome to VB 2023, and it starts process calculator. After compiling this application, we have two ways how we can modify the original IL code. Either we can use some GUI-based tool like dnSpyEx, or we can use some programmatic approach. I will get to that later on. So using dnSpyEx, we can just open the ready-to-run assembly in dnSpyEx. We will edit the IL instructions that are related to process start method invocation. And finally, we will save our patch module. We need to be careful about preserving the .NET metadata, and also we need to remember that we need to check mixed mode module option. I will explain it later on. Here we just open what we already programmed, so just very easy C# code popping calculator. Here is the patching in dnSpyEx, very simple, just we can see before and after. We will just find those three instructions that are related to the process start method invocation, and we will knob them. We can completely remove them, but for this scenario, I decide to knob them. And after that, just saving the patch module. Again, preserving as much .NET metadata as possible, and the mixed mode module option need to be checked. Why? The mixed mode module option is actually propagated to the .NET directory characteristic, and there is a flag, which is there is characteristics flags, which is called IL only flag. And once you here check the mixed mode module, this IL only flag will be unchecked, because IL only flag in .NET assembly means that the .NET assembly contains just IL code, which is not true in ready-to-run assembly. Yeah, so the unchecked option of the .NET assembly of IL only flag is for ready-to-run assembly format, engine file format, or mixed mode assembly file formats. And mixed mode assemblies are the combination when you are programming C++ and .NET. Here is the view of, in dnSpyEx, again, we are checking our already ready-to-run stomped assembly, and we can compare the IL view and C# view. And we can't see any kind of reference or method invocation of some calculator process. But once we try to execute it, we will trigger the precompiled native code, absolutely ignoring the difference to the patched IL code, and process calculator started. The programmatic approach using dnlib, I chose to use dnlib, but we can use other libraries that can do that, like asm resolver or mono. But I chose to use dnlib because there is some tricky thing which is called native module writer. And native module writer is able to very easily preserve all native things in our .NET assemblies. So in this case, also our precompiled native code. And very easy is able to preserve all kind of .NET metadata. The code is pretty simple. We can see that I'm trying to just find the method main. In the method main, I'm trying to find the invocation of method process start. And I will just replace this the instruction related to process start with the NOP instructions and save that. Basically, I did exactly the same we already did in dnSpyEx tool. The second way how we can create the ready-to-run stomped assembly is about replacing of the precompiled native code and leaving the IL code intact. So we will create some decoy C# code. It should be large enough because we try to make it simple. Because if the decoy C# code will be large enough, it will result in enough space in a precompiled code. And after that, we have enough space for our shellcode that can easily fit in place of the precompiled code. And we will be using some memory-independent shellcode because it's the easiest solution how we can replace the precompiled code, and we have no dependencies of the original .NET metadata and things like that. After compilation of the decoy C# code, we get some ready-to-run assembly. But the problem is that we need to actually find the location of the method main of the precompiled code, and we need to get some information about the size of the code. For that, we can use a tool which is called R2R dump. This tool is a part of the .NET source code, so it's available on GitHub. But you need to compile it on your own, because if you try to download installation of .NET from Microsoft, it's not a part of it. You need to download it and compile on your own. The R2R dump tool is the most comprehensive tool because it's well developed and supported. And we can see that we can very easily get information about the main method, about the relative virtual address of the precompiled code of the main method, and also the size. In this case, 282 bytes. We will extract these 282 opcode bytes from the precompiled native code. Why? Because we can use the disassembler like IDA to extract those opcode bytes, and we will use these bytes for very simple binary patching. So we will generate our shellcode, 282 bytes. We can use a tool MSF Venom, which is a part of Metasploit framework, and we will just do the simple binary patching. So we already had the pattern of the original precompiled native code opcode bytes. So we will replace those opcode bytes for our shellcode. And once we try to run this application, the ready-to-run stomped assembly, we will trigger the execution of the implanted shellcode, absolutely ignoring the difference to the original IL code, and process calculator again started. Because we compile the shellcode that pops just the calculator, just typical example. Problems affecting reverse engineering. Well, the main question here is like, who would use a different tool than dnSpyEx? Like really, who? When we are just detect that we are dealing with .NET PE, we will use tools like detect easy or exe info. We find out, hey, it's .NET. So we're just heading directly to the dnSpyEx. But I already introduced that in this case, those shenanigans are a little bit on different place. It's all on native layer, so we must go deeper. There are several problems we need to deal with. Regarding the static analysis, we see a different code than the one that is actually executed. Regarding the dynamic analysis, we debug different code than the one that is executed out of the debugger context. And also other compilation formats could be applied to complicate the analysis, to harden the analysis. Regarding the static analysis problem, here is an example of the precompiled code intact. So in this example, we are having the example ready-to-run assembly, the stomped one, where we replace the process start method invocation with some NOP instructions, we can't see any kind of call of a process start method. Yeah, so it's strange. Yeah, it's very hard to analyze it. But still, if we check the .NET metadata type references, there is something remaining. Like literally, there is a process start method that is a part of the type references because we preserved the .NET metadata when we were doing the creating the ReadyToRun stomping. So the question is like, where is the process start method called? From nowhere. This is quite suspicious. But what about in the case where we implanted our shellcode? In that case, there are no more non-reference types because we actually, we didn't modify the original type references and we created some kind of decoy code. So all type references which are preserved are related to the code we can see in the C# view. So in case of implanted shellcode, there is nothing suspicious and quite a bad situation for the analysts. Regarding the dynamic analysis and debugging, dnSpyEx is suppressing the JIT optimization defaultly. So it basically forces the IL code to be JIT again. Why is this happening in dnSpyEx? Why the dnSpyEx is doing that? Why this is defaultly preset in dnSpyEx? It's all because of the debugging experience. If you want to set a breakpoint and you really want to break there, you need to suppress the JIT optimization. Yeah, this is the reason. So this is the reason why dnSpyEx has this preset. So in case of dnSpyEx, there is no execution of the precompiled native code. So the IL code will be compiled again, and it will result in different execution in dnSpyEx and normal execution. We can also mimic the dnSpyEx behavior in normal execution. We can do it very easily via setting the targeted process environment variable, which is called com plus ReadyToRun, to 0. And once we do that, it works basically like switch off and switch on. Yeah, if we set this variable to 0, the execution of the precompiled code will be switch off. Yeah, and if we set this environment variable, the precompiled code will be triggered and the ReadyToRun stomping was successfully executed. This is a little bit out of scope of this presentation, but I think it's important to note it, that we can also apply different compiler settings like single file and self-contained. And this will harden the analysis even more, that we have in normal situation when we compile the ReadyToRun assembly, it will result in a DLL, which is actually the ReadyToRun assembly, but we have also some kind of executable file, exe file, that's a starter of the ReadyToRun assembly of the DLL, and we have some configuration files that are needed for .NET runtime. And in case we compile the single file, all these files are bundled into single executable file. If we also decide to select the option of compilation self-contained, what happens is that all .NET runtime is bundled into the single file too. So it's very easy to deploy this application to some operating system that the .NET runtime doesn't have to be pre-installed there, because we already bundle it together to one single file. Of course, the complication is that we need to firstly extract the bundle to analyze the ReadyToRun assembly. But we can very easily do that with tools like ILSpy, .peek, or with programmatic approach by ASM resolver. We can see a picture where I am doing that in .peek tool. Regarding the techniques and tools to reverse engineer ReadyToRun assembly, as I already showed you, all the hard things are on the native layer, so we need a different tool set than when we are dealing with ordinary .NET assemblies. And we need these kind of different tools for particular tasks. And these tasks could be summarized as, we need something for parsing the ReadyToRun assembly structure, we need something for showing the IL code and the decompiled C# code, and we need also some tool that is able to locate and disassemble the precompiled native code. Parsing the ReadyToRun assembly structure very easy via tool R2R dump. Again, little recap, it's a part of .NET source code, so you can download it from the GitHub. we can get information like ReadyToRun header structure, sections, and we can also get information about what all methods were precompiled, what are their locations, and what are their sizes. Showing the IL code and interpreted decompiled C# code is very easily, and a lot of people already know that you can use dnSpyEx. But under the hood of dnSpyEx actually runs ILSpy engine. So you can use for the decompilation of the for the C# view and IL code view. So you can also use directly the ILSpy. And locating and disassembling the precompiled native code very easily, again, R2R dump tool. A most comprehensive tool, and we can get the information about location and size of the precompiled code, but we can also let him know that we want to show the disassembly. Not so known that we can do exactly the same in ILSpy tool. We can locate and disassemble the precompiled native code. So we can do that very easily. We will select just one method, and we need to switch the view to ReadyToRun. Yeah, so no C# view, no L view, but ReadyToRun. And we can see that we see the disassembly view. Detection. Firstly, we need to talk about how we can detect the ReadyToRun assembly format. We can do that with tool like .pic or ILSpy, and we can see that once we open a ReadyToRun assembly .pic, it will immediately tell us that it's ready to run, and some information regarding what compiler was used to produce this ReadyToRun assembly and what .NET runtime was used. We can also do this detection via Yara. Yeah, very simple Yara code, which just validates that we are dealing with PE, that .NET directory is a part of this PE, and that the .NET directory contains managed native header, and that this managed native header points to the R2R, which is a like magic signature of ReadyToRun assembly. And if all conditions are met, we are dealing with ReadyToRun assembly. Well, there is nothing like all-in-one solution to analyze or detect the ReadyToRun stomping, but the closest to this is ILSpy. So here we can see a not stomp, again, not stomp ReadyToRun assembly. We can see the C# view, IL view, and disassembly view. We see nothing is strange. Yeah, we see what we can see in C# view and IL view. We also can see in the disassembly view. We can see typical prolog, yeah, because it's the start of the main function. And we can see also the call, the method invocation. And ILSpy is good enough that it is able to resolve us the reference, like where the call is directing to. Yeah, the type references. So in this case, we can see the console write line. What about case where we have implanted our shellcode? In that case, we see C# view, okay, IL code, okay. But what about this disassembly view? We can't see the typical prolog. And of course, we can see some shellcode, Windows-specific shellcode instruction for PEB, process environment block manipulation, to get some memory addresses of DLLs, and probably doing some runtime API resolving. So it's very suspicious. And in case of the patch IL code, we see nothing strange in C# view, also in IL view. But if we check the precompiled code, the disassembly view, we see another call which is there in addition, and this call points to process start method invocation. And I'm asking myself, like, why I can't see this method invocation in C# view and IL code view? Yeah, so this is suspicious. And I think now it's demo time. So in this video, I will show you just I will compare the dnSpyEx and normal execution. So we will just simply open the ReadyToRun stomped assembly. It's the stomped one. And if we check the main method, we can see that just basically printing only simple line or 2 lines. They're like no code bro, some looks good to me. And when we try to debug this, we won't see anything suspicious. Yeah, basically what we can see is executed. So everything is as we expected. But
Can you change that to the light theme, not the dark theme? I think it might be easier to hear.
It's a video.
Oh dear. I thought you were moving that mouse
Sorry, once more. Yeah. So after that, we can also check the typical .NET shenanigans. Like we can see that there is nothing in a module type, there is nothing in program type, because there are no constructors. Yeah, in a .NET, normally the constructors are used to run some code before the main entry point, and they can actually like modify the main code. Yeah, but nothing like that is here. Yeah, everything looks very good, nothing suspicious. But what about if we try to execute it in a normal execution? If we try to execute it in a normal execution via issuing a command like .NET or with the host bootstrapper, we will see something absolutely different. First of all, different text got printed. And the other thing is that some pig popped up that is actually giving us some hint about maybe what should we focus on. Yeah, I think that it's all from my presentation. I would like to thank you for your attention, and let's leave some space for questions.